Hello, everyone, and welcome to Quarantech Tuesdays, featuring today's webinar, Novel Solder Paste to Meet the Challenges of Electronics Industry. My name is Jeremy Glanzer, and I'll be your moderator today. I work with the marketing team here at Blue Ring Stencils, Nanoslick, and FCT Solder, and I'm excited to welcome you to today's webinar. As we wait for everybody to come into the meeting, I just wanted to introduce today's speaker, Tony Lentz. He's our field application engineer with FCT Solder. We are excited to discuss some challenges and solutions that electronics assemblers are faced with the high reliability applications and markets. If you have joined us for past webinars, you know the drill, but if this is your first time with us, I just want to cover a couple things. First, today's webinar will be recorded and will be available on demand after the session. Everyone that's attending today and those who have also registered will receive an email tomorrow with a link to the recording. Also, we would love to hear from you during today's presentation. So if you have any questions for our speaker, please feel free to send it through the Ask Questions tab, and we'll be answering questions at the end of the session. If we don't get to your questions during today's webinar, we'll be sure to follow up afterwards, or feel free to contact us directly. So we've got some people still coming in, but we won't wait any longer. So let's begin the presentation. Tony, you have the floor.
Thank you, Jeremy, and thanks everyone for attending today. We appreciate that. This presentation is about a novel solder paste which has been designed to meet the challenges of the electronics industry. First of all, let's talk a little bit about the evolution of electronics and where we're using electronic devices and where they're headed in the future. Of course, we've all heard of 5G. That's the new latest communication standard that includes increased speed, better signal strength. Of course, transferring large amounts of data in a fast, short period of time is the goal here. And we are definitely heading down the road of Internet of Things, where we're connecting more and more devices to the internet than we ever have before. For example, like kids' toothbrushes, so you can monitor how long and how often they're actually brushing their teeth. Or your refrigerator, so you can pull up a video of what's inside the fridge when you're at the store. If you forgot to buy that gallon of milk, you can go shop for that while you're out of the house, or turning on your lights while you're not home. I mean, it's amazing all the things we've got connected to the internet these days. So of course that demands greater technology in the electronics that are used for these communication and networking equipment. Global 5G adoption trends are also rising pretty dramatically. As you can see in this chart on the right, here in 2021, they expect roughly 600 million worldwide smartphone subscriptions that are 5G capable. And in the next 5 years, that's going to go up to over 3,300 million subscribers. That's a huge increase in 5G usage. And with that increase, of course, comes all the hardware that's necessary in order to make that work properly. Here's a couple of trends for microprocessors and transistors on microchips. And so this chart on the left is 42 years of microprocessor trends from 1970 up through 2020. And if you just look at the orange triangles here at the top, you can see the number of transistors in the thousands has increased dramatically since 1970 in their inception. You know, you might have had 10 on a microprocessor. Now we're looking at 100 million or 100 billion. It's amazing how much technology we're cramming into our electronic devices. And with that, of course, comes increased density of the electronic device. We're cramming a lot more components with higher functionality into a smaller footprint. And then on the right, we've got a chart showing Moore's Law, which is the number of transistors on a microchip doubles every 2 years. And this ranges from 1970 to 2020. And you can see the increase on this as well. It pretty much follows the microprocessor trend data. So the point is that we are demanding more of our electronics and putting more electronic devices in more places. So that requires a lot of circuit boards to be built. And these circuit boards are quite often very challenging. And they're challenging for solder paste, they're challenging for component suppliers, and for all of us who are involved in supplying to that industry. So here are some of the challenges that we face when building these type of electronic devices. First of all, we're using larger BGA components than ever before. The size of the BGA components is increasing, which unfortunately gives more functionality, which is good, but it lends itself to potential problems of warpage related head on pillow. Voiding is a potential issue in BGA spheres like what's pictured here in the bottom. So there are definitely issues that come along with using larger, more highly functional BGAs. We've seen the adoption of bottom terminated components. They're pretty widespread. And unfortunately, bottom terminated components, just because of their physical design, lend themselves to voiding in solder joints, which can create its own problems with the function of that circuit board. And then we're also putting electronics into potentially harsh end use environments. For example, electronics that are stored outdoors or under the hood of a car or even in space. Those are fairly harsh conditions under which that electronic device has to function properly for its life. And therefore, the reliability of the circuit board is key. And thermal cycling is one potential issue from that, especially if you've got a circuit board outdoors. It's going to be cold in the winter and warm in the summer. And then when that device is powered up, of course, how hot does it really get? But those things can potentially lead to solder joint failure. And then one of the other challenges that we face is circuit board designs. We see a lot of mixed technology designs where we've got large thermally demanding components like these heat sinks here on this picture on the right, placed directly right next to smaller passive chip components like these guys over here. And so you've got different thermal demands for reflow profiling that circuit board. It makes it very difficult, as well as different solder paste volume requirements. And so these are some of the challenges that we face building these type of electronics. And of course, the solder pastes have to meet those challenges. Here are a couple of challenges that come along with telecom and network infrastructure electronics. Well, I talked a little bit about harsh environments. Well, think about the environment in space for a communication satellite. That circuit board has to be pristinely clean, sealed, and able to function without being damaged by the radiation or exposure to the vacuum of space. And then also, I would think of this communications tower as a harsh environment. It is outdoors, subject to temperature extremes, and also wind, rain, snow, all types of environmental effects could occur to cause those circuit boards to fail at some point if they're not protected properly. And then of course, what about the theory that 5G causes viruses like COVID-19? Now, I don't have an opinion on that. I just present that as an interesting idea. I'll let you all decide whether that plays a role or not. Certainly, when we formulate solder paste, we can look at all of these things, and we want to try to meet these challenges with our solder pastes. Here's a little more information on BGAs and why they warp and how that leads to head and pillow. So BGAs are, like I said, are increasing in size. I've seen BGAs in use of up to 2.5 inches square, which is fairly large. And they're testing BGAs upwards of 80 to 85 millimeters. So that's almost 3.5 inches square. That's a huge component if you think about it. And all those solder spheres on the bottom of that component have to make proper solder joints. Well, during reflow, BGAs tend to warp, like what's pictured here. So during the soak or the ramp up part of the profile, you can see this BGA diagram. It's warping up off of the circuit board and it's pulling some of the solder paste with it, or completely separating from the solder paste. And then once the solder goes liquid, the balls will melt individually and the solder paste will melt, and it's not in contact with the sphere of the BGA, and therefore they'll never merge together properly. And so when that component cools down at the end of the reflow profile, you've got this situation where you've got the sphere and the pillow of the solder paste just separate from each other with a dividing line. And that may or may not be making electrical contact. So that's definitely a source of failure with using larger BGAs. And larger BGAs are more susceptible to that problem because the larger they are, the more warpage induces curl or potato chipping in that component. Bottom terminated components are obviously commonly used in our industry. We've got a picture of a QFN here that's pretty standard. There are DPACs and then also QFPs with a thermal pad on the bottom. Of course, with these comes the challenges of how to get the right amount of solder paste in order to make a solid connection to all of those contacts, especially the larger plane areas like what's pictured here. So this is an example of 3 different ways to print solder paste onto the thermal pad of that QFN. These are all 70% area of coverage, and it's just 3 different theories on how to break that paste up. But the point is you can see how large the ground plane part of that component is compared to how much paste you have to put down. There's a relatively large amount of paste going down there. And when that paste creates volatile gases during reflow, those gases can't escape out of the top because the component is flat, and it basically prevents the gases from moving to the top of the solder joint like they would naturally want to do due to the relative densities of the solder versus the gas. So the gases have to try to escape out the side, which is a relatively long trip from the center of a QFN to the edge. So that tends to lead itself to voiding. And so the solder pastes that we create have to be created with respect to minimizing voiding potential for these types of components. Voiding can lead itself or lend itself to these types of failures. There's potential for overheating failure, like what's pictured here. One of these D-packs overheated and actually burned the circuit board. And I don't know if that was specifically due to voiding, but that's certainly one potential. If there's large amount of voiding in that thermal solder joint, then the component's not able to wick heat away quickly enough, and this could happen. The BGA sphere on the right shows a void-induced crack. You can see that void is actually fairly large compared to the BGA sphere, and it definitely cracked at some point in its life. So voids can definitely cause some problems in solder joints. What about harsh environment and the reliability of solder joints? I was talking a little bit about electronics that are used outdoors, where here's an example of winter versus summertime. The air temperature could range from, say, -40 centigrade to +50 centigrade in extremely hot climates. But the board surface itself probably will get down to -40 centigrade based on whatever the outdoor winter temperature is. But when you power that up and it generates some heat from its use, it could easily get up to 125 C or higher, which is why we use that temperature range for reliability testing quite typically. But with that thermal cycling over a period of time comes fatigue, and eventually the solder will crack, or the different coefficients of thermal expansion between the component, the solder joint, and the board surface just eventually induce cracking in solder joints. And so that's one potential problem for electronics that are used outdoors or in harsh environments. Different component sizes that we use on mixed technology boards also create some challenges. Like I mentioned earlier, we've got a fairly large component here versus some pretty small components which have totally different solder paste volume requirements. The large component requires a lot more solder paste. And when you reflow that, this large component is going to act like a heat sink. And so it can be quite challenging to get the appropriate reflow temperature for the solder paste underneath the larger component, as opposed to trying not to overheat the solder joints on these smaller passive chip components. So a couple of things we can do to help with that are use of step stencils. If we use a step stencil, we can obviously increase the volume with a step up in a certain area. But as soon as you increase the thickness of the stencil, you have effectively reduced the area ratio of those apertures, which may present a printing challenge for the solder paste. And then the same holds true for the thermal profile. You can obviously use a silk profile, give it a really slow ramp up to peak in order to heat up all of these components equally. But not all solder paste can handle a long, hot silk profile. And so when we formulate new solder pastes, we have to think about these things. We have to make sure that can print through a wide range of area ratios, as well as handle a wide range of different profile conditions. So here's some information about a new solder paste that we worked on in order to meet these challenges. The requirements that we used specifically for this solder paste, besides what I've already mentioned, we want to make sure this solder paste has some potential to reduce head and pillow. And we did that through increasing the activity of the solder paste, which helps to remove oxides on the BGA sphere, as well as within the solder powder itself. That helps to ensure that these solder deposits will merge properly during reflow. We can adjust the rheology of the solder paste, making it a little more elastic so that it will stretch. So if a BGA warps and pulls the sphere up out of the paste deposit, the paste will have more of a potential to stretch along with it and stay in contact with the BGA sphere rather than snapping back to the board surface. And then we also want to make sure the solder paste can handle a wide thermal profile window, like I mentioned on the last slide, so that we can minimize warpage in BGAs by using a silk type profile in order to slowly heat things up, and hopefully the BGAs don't warp as aggressively under those reflow conditions. In terms of voiding reduction, we formulate solder paste in order to minimize the potential for voiding. Obviously, there are a lot of different sources of voiding that can range from the circuit board materials to the component surface to the board design. There's so many things that influence voiding, but the solder paste, as I've always said, sets the baseline for voiding potential. And so we try to minimize that voiding potential by using higher activity in the solder paste to remove oxides and to promote wetting and flow. So the voiding is caused by two major things. Either the solder paste doesn't wet and flow completely and leaves a gap in the solder joint, either at the component interface or the board pad. And that, by its very nature, that gap in the solder joint is a void. And the other thing that solder pastes do is they create gases during reflow. And so we can switch the solvents and use different rosins that specifically minimize gas generation during reflow. And together, those solder pastes can then produce very low voiding levels compared to what we've seen in previous generations of solder paste. In terms of reliability, there's a couple of things we do with solder paste formulations. The first thing is we try to make them halide and halogen free, especially for no clean fluxes, so that there is no potential halide or halogens on that surface, which could potentially corrode or cause dendritic growth to the metal surfaces. We also want to make sure these solder pastes pass all of our industry standards for SIR and ECM, including IPC-J standard 004, JIS 3197, and Telcordia GR78. And all of these test methods have different test criteria, slightly different circuit board designs. And so it's quite a rigorous set of tests, and that we ensure that new solder paste can meet all of these criteria and pass those tests very well, so that the flux is benign, at least as benign as it can be when you leave no clean flux on the circuit board surface. And then in terms of reliability of the solder joint itself, that's more of a matter of what the solder alloy is doing. And so in this particular case, I'm showing Inalot versus SN100CV. SN100CV is a new solder alloy, relatively new, that we're promoting in our solder pastes. And it was designed to give higher reliability test with certain types of tests versus things like Inalot. And so in this particular case, the blue dots here show the SN100CV Weibull plot, and it lasted longer through more cycles than Inalot did in this particular test. The other alloy that we are marketing for high reliability applications is called LFC2. Now, choosing high reliability alloys will definitely increase the solder joint life, especially for harsh environments. And if we're talking about like something that has to go into space or is outdoors or potentially under the hood of an automobile, you've got a lot of thermal cycling going on under the hood of a car and a lot of vibration as well. And so you have to use the right solder alloy for those conditions in order to ensure that the solder joints last as long as they're designed to. So the solder paste that we worked on also has to be able to print in a wide area ratio range. And so we've got an example here on the left of transfer efficiency versus area ratio. And these area ratios that we test normally range from 0.30 up to 0.80. And in this particular chart, we're showing three different solder powder types: SAC 305, type 3, type 4, and type 5. And what we want to do with this test is see where the transfer efficiency minimum, or where the area ratio minimum is, that allows us to get 70% transfer efficiency. And so we formulate solder paste to print through lower area ratios and test them through this type of a test. And so we really challenge the solder paste by taking them all the way down to a 0.30 area ratio. The other thing we do is we run our solder paste through a wide range of reflow profiles. And we use a variety of materials in the solder paste in order to help broaden this window for reflow profiles. So this particular reflow profile example is from J standard 020, and it just shows you what's normally used in our industry. I mean, we have very short cool profiles ranging to long hot profiles. Sometimes we use relatively long soaks. Sometimes there is no soak and it's a linear ramp to peak. And we want to make sure that our solder paste can run in all of those profiles because they're all used in the variety of electronics that are built. Some other things that we look at for new solder pastes is we want to make sure they have good small deposit coalescence. That means they aren't going to create graping. So this is a test pattern that we commonly use, and the area ratios that we're printing through range from 0.35 up to 0.70 on these patterns. And the smaller patterns, by their very nature, tend to be more susceptible to graping because you have a very small solder paste deposit with a relatively large surface area of solder powder in the paste, which can oxidize during reflow. And the paste flux has to protect that from oxidation and have enough activity to remove the oxide so it coalesces properly. And so we always run this test as part of our R&D on new solder pastes. We also wanted any new solder paste to be pin testable. For anyone who's doing in-circuit testing or flying probe testing like this, we want the flux to be soft and pliable for at least up to 5 days so that circuit boards that are queued up after assembly can be tested later on. And then we want the solder paste to work with pin and paste applications. We still see our customers using this a fair amount. If you have, say, one connector on a circuit board and the rest of it is surface mount, it makes sense to try to use pin and paste reflow for that connector, for that through-hole soldering, if you can get away with it. So here's some test data on this novel solder paste. First of all, we run a print and pause test over a period of time. And so this particular paste was printed over an 8-hour window, and it has pauses of 1 hour, 2 hours, and then 4 hours during the test. We want to make sure that the solder paste transfer efficiency here doesn't drop off after any one of these pauses to make sure it's not drying out in the stencil. And so in this particular case, we have optimal printing over the 8-hour print and pause test. And then in terms of reflow performance, here's a comparison of the new solder paste, which is the blue bars, and a comparable solder paste, an older generation, is the orange bar. So wetting had much improved with the new solder paste, as well as solder balling and graping. All of these, higher is better on this particular chart. And so we were able to improve all of these reflow characteristics with the new solder paste formulations. And then lastly, we measure voiding with QFN components typically. And this new solder paste was designed to give ultra low voiding. And so we typically see voiding like this down below 2% void area on a 10 millimeter QFN. So out of all this work, we created a new solder paste in our process amplifying series that we're calling AMP1PT. That's all I have for this webinar. Thank you for your attendance. We really appreciate it. And now we have time for questions.
Thanks, Tony. As always, you do a great job of laying out all of that and all of your work. So I appreciate your time. Now we want to open up the floor to some questions if anyone has. Looks like there's a couple that came through already. Jazzbeer asks, what is the thermal cycle profile used for SN100CV and the component used? It might be a little specific, but
well, SN100CV specifically has a melting range of 221 to 225, but in terms of like a thermal cycle testing for reliability, we would use -40 to 125 C for that, typically. I don't know if that answers Jazzbeer's question specifically, but the peak temp in a reflow profile, if he's asking about that, would be 240 C roughly.
Thanks, Tony. We got another one in here. This was kind of mentioned, but does this solder paste work well for other industries like automotive, military, and aerospace applications?
Yes, it certainly does. It would be applicable for any industry. It was designed to meet the needs of a variety of industries, so that it can be used sort of as our main go-to solder paste.
Right. We've got one from Ravi. How does it compare to regular AMP1 from cleaning standpoint? Will it make it easier, difficult, or be the same?
It's a great question.
Mm-hmm.
The flux residue is a little bit different because it's pin testable. Regular AMP1 tends to harden after a couple of days. It becomes quite brittle. And after that period of time, I think AMP1 could be more difficult to clean. The AMP1 PT flux residue stays soft and pliable for a longer period of time. So I believe it would be easier to clean, especially if you delayed cleaning for a few days.
Mm-hmm. Let's see here to follow up with Jazz Beer. That's good. What was the soldered component used for the thermal cycling? Excuse me.
Those were resistors. I want to say they were like 1205 size, 1206.
Okay, thanks, Tony. Let's see, a couple from Tim. What would be the temp and humidity required in the paste printing process machine with this paste? Do you need to mix it?
We recommend kneading or shear thinning the solder paste before use, just as a general rule of thumb. That's a good practice because we really don't know what the storage conditions were or the shipping conditions of the solder paste. And so if solder pastes get frozen or if they get too warm during transit or during storage, sometimes they can thicken up a little bit. And so it's always a good practice to mix or shear thin, although this paste doesn't necessarily require that. And then inside of the printer, we recommend pretty standard conditions. I mean, anywhere from say 30 to 75% relative humidity. And in terms of room temperature, roughly 60 to 80 Fahrenheit would be ideal.
One from Surge, which I know the answer, but I'll let you take it, Tony. Is the AMP1 also available with tin lead alloys?
It is not. It is not designed for tin lead soldering. That's a good question.
Yeah. Let's see, one from Tyler. What reliability testing has been done on AMP1 PT solder paste?
Well, we have done all the battery of tests that I listed, the JIS, Telecordia testing, and IPC, SIR, and ECM tests. All 6 of those tests were done, and it passed with flying colors.
Awesome. Let's see. When will this solder paste be available?
It's actually been in the market for some time, so it is available now.
Yep. Got another one. What type finish PCB was this test performed on? So I'm assuming the surface finish.
Yeah, normally we run our internal R&D on ENIG, and then we also check it on OSP, sort of as the best case and worst case scenarios in terms of wetting and reflow.
Right.
And typically we don't see a large difference in voiding between those finishes, but we do see a difference in the wetting behavior, of course. And sometimes graping and solder balling might be affected, but that's not typical. Of course, our customers are using the solder paste in a wide array of surface finishes.
Right. Another one from Surge. Is AMP1 paste available with type 5 powder?
Yes, it is.
Awesome. Thanks for the questions, guys. Does anyone else have any other questions for Tony while he's on? Again, if you have anything else or you think of anything, after this, feel free to contact him directly. Or you can reach us through, fctsolder.com as well. Any other questions? Awesome. Well, thanks for everyone's participation. Really appreciate that. It makes these webinars a little bit more fun and we can have some discussion. Serge came back and said, why are tin lead alloys not available for AMP1?
Because we have an excellent tin lead no clean solder paste called NC676. That's the short answer.
Yeah, Serge, check out NC676. Awesome. Well, thanks everyone. Like I said, feel free to reach out. We're available anytime. As I stated, Tony's always looking to present new topics and working on new challenges. And so we'll definitely have something, slated for our next Corn Tech. We've changed the frequency of our webinars to monthly now. So definitely be on the lookout for the next topic. Looking forward to seeing everyone in a month. Stay safe and have a great rest of your day. Thank you. And thank you, Tony.
Yep. Thank you, everyone.
Goodbye.